I just realized it doesn't line up.
Okay, so what you should notice as you take these derivatives is in the numerator, you're basically building factorial because you keep multiplying by a higher and higher negative power of x. So you're building factorial here. And then you keep getting a higher and higher power of 3. That should be 3. So and you keep getting a higher and higher power of 3 in the denominator. So that's what happens with these derivatives at 3. It alternates, first of all. It builds factorial in the numerator and builds powers of 3 in the denominator. Did you get that? And if not, do you see it? Do you see any questions on that? Okay, so then what's my first? So f of x, so I'm going to build the Taylor series here. F of x equals, what's the first term? What is it? So this is, we're going to have natural log of 6, right? So when n is 0, natural log of 6 over 0 factorial, which is 1. 0 factorial is 1, right? Times x minus 3 to the 0, which is just 1. Okay, next term. It's going to be our 1/3 over 1 factorial times x minus 3. Keep going like this. Next one's going to be minus, right? Is it still 1, right? Minus 1/9. Or 1 over 3 squared over 2 factorial times x minus 3 squared. Is that right? Plus, we'll do one more and then we'll do the general term. So one more would be 2, and we know that this 2 is really 2 factorial, right? So it's 2 factorial over 3 factorial. Sorry. 2 factorial over 27, or 3 cubed. So we get 2 factorial over 3 cubed over 3 factorial times x minus 3 cubed. So the nth term then is, so it's alternating first of all, and so when n is 1 we get positive, when n is 2 we get negative, when n is 3 we get positive. So how do we do that? Negative, it's negative 1 to the n plus 1. So we want the so we want the odd ones to be positive, right? So whenever n is odd, it makes us positive. Okay, so negative 1 to the n times. So that is what? N minus 1 factorial, right? So in the third term, we have this n minus 1 factorial. So that's, notice this, 6 gives 5 factorial, 5, 4 factorial, 4 gives 3 factorial, divided by 3 to the n. We always have n number of 3's, 6 3's, 5 3's, 4 3's, 3 3's in the denominator. And that's over n factorial times. Okay, so now can that be simplified at all? In fact, it can. This n minus 1 factorial and n factorial all ends up being just n in the denominator, right? Because n factorial is n times n minus 1 factorial, right? It's n times n minus 1 times n minus 2. Well, as soon as you get to n minus 1, you build n minus 1 factorial. So this all here just becomes n in the denominator. So that just all goes to 1 over n. Now, what do you notice here? What about this? The ln of 6 to start with. Is it what you get when you plug n equals 0 into this? No. So we need to kind of pull that aside. The real pattern starts after when we take the first derivative, right? That's where the real pattern starts, with the derivatives. The 0th derivative just gives us a constant that really doesn't relate to the pattern that builds. So when we write this function, we have to separate that out. So we're going to have f of x equals, we're going to start with natural log of 6, and then plus summation starting from 1, and then we can write it. So it's going to be, we alternate this way. Our denominator is n, and there's also 3 to the n in the denominator. So this all makes n in the denominator. We got 3 to the n in the denominator also. And then x minus 3 to the n. So there it is. There is the Taylor series for ln of 2x centered at 3. So did anyone have that before I did it? Everyone get that, or most of it? Most of it? Okay. Over here. All right. So hopefully you got most of it. All right. Now the question is, what's the radius of convergence? What's the radius of convergence? How do we find that? Ratio test. So we do the ratio test on that and find the radius of convergence, and then also test the endpoints. Test the endpoints. Go. Your task. Find the radius of convergence for this series. The limit in the ratio test, what did you get? 1 over x. X minus 3 over 3. That's what you should have gotten for the limit. X minus 3 over 3. When you do the ratio test, you should have gotten x minus 3 over 3 as the limit. And then what do we do with that limit to get the interval convergence? Yeah, so we know that the ratio test is all about if this series is becoming a geometric series, and we need that multiplier to be between 1 and -1, or the r, kind of the r value. So we're going to do x minus 3 between 1 and negative 1. And so then we get x between 6 and 0. You do the math, right? Multiply by 3, add 3. Okay? You get x between 0 and 6. Any questions about that? Did some of you get that? So we've got some thumbs up. Okay. And then we can check the endpoints. So what about 0? If we plug 0 in for x, the 3 to the n's go away. I think it's harmonic. Oh, no, wait a sec. Because it's the n and the n plus 1. You plug in 0, you get negative 1 to the n plus 1 times negative 1 to the n times 3 to the n. I just split those apart over 3 to the n, so that goes away. So what is this? Negative 1 to the 2n plus 1. It's always negative. All right, so this is, you get negative 1 to the 2n plus 1. That power is always negative, or always odd. Right? That's an odd power. So you're always multiplying by negative 1. So we get the opposite of the harmonic series. So this is basically just negative 1 times the harmonic series. So we don't include 0. Okay? So what I did, I plug 0 into here. If I plug 0 into here, I basically get this. You get this series. Because you end up getting 2n plus 1 negatives 1s, which is always an odd number of negative 1s, which is negative 1. Okay, and you plug 6 in, you don't have this. So you have 3 to the n, so you don't have that. And now it alternates. So your 3 to the n's go away, and now you have the alternating harmonic series. So it converges at 6, but not at 0. 6 gives you the alternating harmonic series. 0 gives you the opposite of the harmonic series, which is just harmonic times negative 1. So there's our interval of convergence. Okay, any questions on that? Okay, so let's talk about, so this function, the function is, ln of 2x looks like this. So we talked about how Taylor polynomial, so the Taylor series then will reproduce this function perfectly. If we were able to add all infinitely many terms together, we'd get this function perfectly. Would we get it perfectly everywhere? Where would we get it perfectly? Everything greater than 0 up to and including 6, right? We said greater than 0 and up to 6. So from all of this up to here, it's going to, this Taylor series will reproduce that part of natural log 2x perfectly. So now what about Taylor polynomials? So so our first Taylor polynomial is ln of 6. What does that do? What does that do for us in terms of the original function? So this is t0. T0. What does it do? Horizontal line. And that horizontal line, what does it accomplish for us in terms of estimating the function? What does it get right? So I think a lot of you are saying, it just gets natural log of 2x at x equals 3. And so that's why it's natural log of 6. So let's show that. Do that in red. So here is t0. Here's the first Taylor polynomial. The only thing it gets right is the value of the function at our center point, right? We built this Taylor polynomial around 3. So the only thing that t0 gets right is the function value at 3. All right, what is t1? But so what is the first Taylor polynomial? So a lot of you were struggling in the homework, and you said that the first Taylor polynomial was this right here. So when it asked you for Taylor polynomials, you were just putting in just single terms of the Taylor series. But remember what the Taylor polynomials is, what they are. What's T1? T1 is ln of 6 plus x minus 3. So it's the constant and the linear term. That's what T1 is. It's not, the first Taylor polynomial is not just that, the linear term. It's the whole partial sum, right? Taylor polynomials are partial sums of the Taylor series. So what will T1? So when I graph T1, what will it get right? It'll still get the function value right, but then also, what's the little bit extra? Okay, so and what does the tangent line get right that this doesn't? First derivative, right? The first derivative. I hope this works. There we go. So there's the first Taylor polynomial, which is two terms, right? It's the constant term plus the linear term. And that gets the function value right, and it also gets the first derivative right. Okay, what about T2? First of all, what is T2? And what will the graph be like, and what will it get right? Tell the person next to you. So three questions. What is T2? What is the second Taylor polynomial? What does it get right? What will the graph look like for T2? Go. Talk to the person next to you. Okay, first of all, what is T2? What is T2? Let's see here. Jamie. Good. So T2 is the partial sum up to the quadratic term. That all is T2. Or in the web work, they also call it P2. All right? So T2 of x, right? It's a function, T2 of x. Or P2 of x. Okay? What will it get right? What will it get right? Maxim.
We'll get second derivative.
Right. It gets the function value. It gets the first derivative and the second derivative right. And then if I graph P2 or T2, what will it look like? What will it look like? Samantha? Quadratic? Yeah, so quadratic approximation, which is a parabola, right? So we're going to get a parabola that approximates at 3 and gets the first derivative, second derivative, and function value correct. All right, so then as we know that, so what would T3 be? T3 would be the sum of all those terms I'm showing there. The first four terms would be the Taylor polynomial. T3, it's going to get the first three derivatives correct, and it's going to be a cubic function that approximates the original blue graph. So now if we take higher and higher, each time we take a higher Taylor polynomial, we get more derivatives right at 3, and we get a better and better approximation around 3, right? So there's 4. There's the fourth polynomial. Fifth, sixth, and where is it going to converge again? From where to where? 0 to 6. So to the right, watch what happens to the right of 6 as I keep taking higher and higher Taylor polynomials. Greater than 6, it's not going to converge on the function. It's just going to keep flipping up and down, whirling off to infinity for greater than 6. So here's the 20th. Here's the 20th Taylor polynomial. And what do you see? You see like from like a half or a quarter all the way to almost 6. It's black, meaning it's doing a really, really good job now estimating the function in the interval of convergence.
If the Taylor series was centered at a greater x value,
Yeah.
would it have a greater radius of convergence?
Yeah, so for instance, if we had centered this Taylor series at 7, if we had centered at 7, then all our Taylor polynomials would be centered at 7, would get this function value right, and all the derivatives right here. And then our radius, it would turn out, we would have what, x minus 7 to the n, over 7 to the n, and then our interval would be 0 to 14. Yeah, so we'd get, if we centered at 7, when we did the limit in the ratio test, we'd have x minus 7 over 7 instead of x minus 3 over 3.
I see, yeah.
And this is going to take us from all the way now from 0 to 14.
But that's only for natural, that's not wrong.
This is just for natural log, right? This is the way the natural log works out. Right, so she said if we picked a higher value of x to center about, then we get a bigger radius, because we're always going to get from 0 out to like twice the value of the x value that we choose to center at. Okay, what I'll do is I'll just go ahead and reopen the web work, because I know lots of you didn't get them all, so because I know this was hard. So I'll reopen the web work to be due Friday morning, okay? And I'll give you like 5 more attempts, okay?